Hello, and welcome to our fourth snow day lesson on thermodynamics. Today we're going to talk about the first and second law of thermodynamics. We are going to talk about what work is and how do we calculate work in a thermodynamic system, and we're going to talk about heat engines. Back to our big conservation of energy diagram. Before we talk specifically about the types of energy, the kinetic and the potential energies and the thermal energies and the chemical energies, but now I'm going to start to refer to these as the internal energy. Remember, the internal energy of a system is made up of the potential energy of the system and the kinetic energy of the system, even the thermal energy of the system. And we've talked many times about how in order to change the energy of the system, we either need to do work on it. We just started talking about how we can transfer heat into it, or we can lose energy from a system by the system doing work or by heat flowing out of the system. That's what we're going to talk about in more detail today, because that's what the first law of thermodynamics is all about. Now, like I said, there are two ways to change the amount of energy in a system, the internal energy of a system. By the way, we symbolize internal energy through a U, a capital U. Right? We said that we could transfer heat into a system, or heat could flow out of a system. If a system gains thermal energy, then that is positive Q. Positive Q means the internal energy is going to go up. If a system loses thermal energy, then Q is negative, and the amount of energy in the system is going to go down. That should make sense, right? If we turn on a hot plate and we transfer energy through molecular collisions into a beaker containing water, right, the thermal energy, the internal energy goes up, right? The temperature goes up, which means the molecules have more kinetic energy. If we let that beaker then cool down, we take it off the hot plate, we let it cool down, right, heat is transferred out of the system, heat flows out, the temperature goes down, right, which means that I'm losing kinetic energy from the molecules. The other way is through work. Now, work can be done on a system or by a system. Work, remember, in terms of force, is force times displacement. But remember that work could be positive, it could be negative, it could be zero. It depends upon the direction of the force and the direction of the displacement. Right? If you remember back to our unit on energy and work, right, if the force is in the direction of motion, then that's positive work. Positive work always increases the energy of a system. If the force opposes the direction of motion, like friction, right? Friction is a good example when negative work is done, because frictional force always opposes motion, right? That's when we lose internal energy from our system. So again, work and heat are processes. They're not states. We don't stick a temperature in and measure heat flow. We can measure the kinetic energy, right? That's what a thermometer does. They're processes. They're transfers of energy. Let's look in a little more detail about work and how we're going to calculate it in the thermodynamic unit. Right? Work is force times distance. And if you remember back to fluids at the end of first semester, right, we related force and pressure to each other. We said that pressure is force per unit area, right, which means that force is equal to pressure times area. So when we're dealing especially with gases, and that's where we're moving now in thermodynamics, is internal energy of gases. If I change that to force is equal to pressure times area, and I substitute that in for force, right, we get work is pressure times area, and again, still have that displacement. Now, if you think about a chamber containing gas, right, we're going to start talking about gases. If I have a chamber, and maybe it's some sort of container, and it has maybe a movable piston, and I apply a force on this movable piston, right, I can compress this. I can make this piston go down so that maybe now it looks like this. Here's my piston down here. I have moved some distance here, x. So I've applied a force on this movable piston, which has forced this piston down some distance x. work being done. Now, if you think about it, this was my original state, right? The piston was out here originally. I moved it some distance x. Pressure is force times area, right? That would be the area of my piston. And if we think about what just happened here, what did we do? We just changed volume, right? Area times x, area times height, right? That's volume. So I can rewrite the area and the x in terms of a change in volume, right? I had a volume that was large here. I applied a force in the direction of motion, right? I did positive work, and that changed the volume. It shrunk the volume of my container. So our equation for work, and really we should call this work on. I didn't put the on there because when you look at your green sheet where the equations are, right, it'll just say work is negative P delta V. But if you think about it, work being done on our final, right, force and direction of motion, we make the volume smaller, so our final volume is going to be less than our initial volume, which is going to end up giving us a positive work. So this is really the equation for work done on a gas. Work done on a gas is negative P delta V. When I do work on a gas, right, I'm doing positive work. I am forcing the piston in the direction of motion, positive work. And so if the final volume is less than the initial volume, and I need work to be positive mathematically when I start doing some math, then I need to stick a negative in there. That will give me the correct positive sign for work. Now, work done on a gas is equal to but opposite of the negative of work done by the gas. So in this case, I am doing positive work by pushing on the piston, but the gas molecules are pushing back. They're pushing this way with a force in the opposite direction, Newton's third law, equal but opposite force, which means it's doing negative work. The force of the gas is this way, the piston's moving that way. So work on is always equal to but opposite in sign of the work being done by the gas. Let's talk about the first law of thermodynamics. The first law of thermodynamics says that the change in internal energy is equal to heat being added or removed to the system, so either positive or negative Q, plus work being done on the system, or minus work being done by the system. So anytime I have heat flow and or work being done, I'm going to change the internal energy of my system. Delta U, the change in internal energy, is equal to Q plus work on the system. Now, what this means is that if heat flows into the system and or work is being done on the system, I'm compressing the gas, then I'm going to increase the internal energy of the system. If heat flows out of the system, the beaker cools, or maybe the gas expands so that the force of the gas is moving in the direction of the piston, then work is going to end up being negative. Final minus initial is going to be bigger, so that's going to end up with a negative. Work done by, then the amount of internal energy of the system is going to decrease. So let's do a calculation. Well, the thing that will mess you up in this unit in thermodynamics, now that we're talking about the first law of thermodynamics, is the sign for work, whether work is positive or work is negative. So one thing you should think about is anytime a gas is compressed, so it's made smaller, that's positive work. And anytime a gas expands, that is negative work. And because you're thinking, well, it's a smaller area, shouldn't that be negative? No, that's positive. So that's why the signs of work will mess you up. All right, we're going to do just a quick calculation here. I have a chamber here containing gas molecules, and I have a movable piston here, and the gas is going to absorb 400 joules of heat. As it absorbs that heat, as heat is transferred into the gas itself is going to do 120 joules of work on the piston. Now, it's doing work on the piston, which means work is being done by the gas. It's going to expand. So I put 400 joules into the system through heat, and it's going to cause the gas to expand, which means there is work being done by the gas. It's going to expand. So our heat is positive, and our work is negative. So by the first law of thermodynamics, then, delta U is Q plus W. Then I have a negative for work because the gas is actually doing the work, so that's work done by the gas. 400 minus 120 gives us a positive 280 joules. Because our answer is a positive 280 joules, that means that the internal energy of our system is increasing. The amount of energy we have contained in this gas is increasing because the amount of heat flowing in is greater than the amount of work being done by the gas. So now let's talk about the second law of thermodynamics. The second law of thermodynamics says that the entropy of an isolated system increases until it reaches equilibrium. What entropy is about the randomness of the system, or how probable a system is to occur. So another way we can talk about entropy is in terms of probability. Now, if you know anything about statistics, the probability of a system being more random is higher than the probability of a system being ordered. For example, if I take the stack of papers, right, and I throw the stack of papers in the air, what is the probability that it is going to land like this in a stack, a nice little stack? The probability of that is really, really small. The probability that it's going to be random and spread out throughout the classroom, well, that's pretty high. So let's try it. So I take my stack of papers, I throw it up, and did it land in a nice little stack? Well, a couple things landed in a stack. The rest of it is spread out throughout the room. So the probability that it's going to spread out and become random is much higher than the probability of it ending up in one nice little stack. Another way we can talk about entropy in terms of thermal energy is that when thermal energy is generated, remember thermal energy is the molecular energy of the molecules in a system, the kinetic energy and the potential energy of the molecules. So anytime we create thermal energy, right, we increase, and when we generate thermal energy and we increase the thermal energy, we increase the molecular motions in a sample, and they become more random, more spread out. So anytime we generate thermal energy, we increase the entropy, and because we've increased entropy, and entropy spontaneously increases, the process is not reversible spontaneously. Now we can make the process reverse, but that's going to require us doing some work or putting some energy in. Another way we can talk about entropy, and another consequence of entropy, is the fact that heat flows spontaneously from hot to cold. Remember when we looked at that simulation in one of our other videos, and we had the two chambers that the molecules had different temperatures. Remember, temperature is a reflection of how fast they're moving, how much kinetic energy they have. Now, the system is not going to stay ordered like that if there's no wall separating the hot and cold molecules, right? In fact, the hotter, faster moving molecules are going to start moving into the colder side, the lower, slower moving molecules, until we get a random arrangement of molecules. So heat always flows from hot to cold because that is a spontaneous process. It's spontaneous for the molecules to move out. Now that will occur, and as they collide with each other, they transfer energy until they've reached equilibrium. Remember, thermal equilibrium, all of the molecules have the same average kinetic energy or the same temperature. So that is the second law of thermodynamics. Now the second law of thermodynamics can be used actually to take thermal energy and create mechanical energy. The problem is the efficiency isn't that great. So we can combine the second and first laws of thermodynamics to generate an engine, and in fact a heat engine. So we can take this spontaneous process of heat flowing from a high temperature to a low temperature, and we can kind of harness that to generate mechanical energy. So this is a very simplistic model of a heat engine. We have a hot temperature reservoir. The temperature of the hot reservoir is symbolized by TH. Down here we have a cold reservoir, a sink for that heat. The temperature of that we call T sub C. And so spontaneously, this hot reservoir is going to generate a heat flow towards this cold reservoir. So I have heat flowing into this engine. We call that Q sub H or Q hot. And some of it is going to flow out here into the cold reservoir. But in the process, we can generate work. Now, a couple examples of heat engines are like steam engines, internal combustion engines. These are very important, especially in the generation of electrical energy for us, right? We have coal plants, and so what we have here is we have a fire, and we burn coal, which produces heat, and that heat flows spontaneously from hot to cold. So in here we have some water at a lower temperature, heat flows in, and I increase the temperature of the water through that heat flow, generating steam, and that steam will turn a turbine, or maybe it pushes a piston, which then causes mechanical energy to be generated. So my wheel starts turning. So a heat engine is any cyclic device that produces work by that spontaneous heat flow from hot to cold. So heat goes in, we have a high temperature reservoir and a cold temperature reservoir, so heat is spontaneously going to flow, and we can use that to harness some of that energy to generate work being put out. Now, mathematically, if we want to know how much work do we generate, well, because of conservation of energy, right, the total energy has to stay constant. So the energy that I'm putting in through the hot temperature reservoir here has to equal the sum of the energies coming out of the energy. So the work plus the cold reservoir. So the amount of work being done, therefore, is the difference between the amount of heat that's flowing from the hot reservoir here, our heat going in, and the amount of heat that gets exhausted that's flowing through our cold reservoir. Now, this can never be 100% efficient because by the second law of thermodynamics, heat spontaneously flows from hot to cold. It can't just go right to work. We can't bypass this part of the engine and completely get all of this thermal energy to generate work. We have to exhaust some down here. The second law of thermodynamics doesn't allow this to be 100% efficient. So how do we calculate the efficiency of the engine? Well, the efficiency of the engine is really just the difference, the ratio of how much work is being done, so how much energy are we getting out, how much mechanical energy are we getting out, divided by how much of the thermal energy are we putting in. So the efficiency of an engine, which can never be 100%, is the amount of work that we are generating, so how much mechanical energy are we getting, divided by how much thermal energy are we putting into the system, QH. Now, of course, we can rearrange this equation if I want to instead. Maybe I don't know how much work is being done, but I know how much heat is being exhausted from the engine, and I don't want to calculate work. We could just plug this equation in for work and do some rearranging and get that the efficiency of a heat engine is 1 minus how much heat is coming out or being exhausted from the system divided by how much heat is moving into the system. So now with efficiencies, of course, I usually calculate efficiency this way, but you'll see this is useful when we're looking at maximum efficiencies. Now, efficiency you can report as a decimal place, or you can multiply that by 100 and report it as a percentage. So let's take a look at some heat engine calculations, very simple. Frequently you see these in multiple choice on the AP exam. Here is my heat engine. It has 920 joules of heat flowing into the engine. I have 630 joules flowing out of the engine. If I want to know the work done by the engine in each cycle, right? The heat engine is cyclical. So in this cycle, I have 920 going in, I have 630 joules of heat being exhausted, and the work is just the difference between 920 and 630. So 920 minus 630 is 290 joules. The efficiency of the engine, now that I know the value for work, I'm just going to take work, 290 joules, and divide by the total energy that I put in, which is 920. So 290 divided by 920 gives me 0.315, or in terms of percent efficiency, 31.5%. So not very efficient. But heat engines can't be 100% efficient. Now, there was a guy a long time ago, Carnot, who was studying heat engines and wanted to make the maximum efficient engine. Now, an engine with maximum efficiency would be completely reversible. And in fact, a Carnot cycle looks like this. We're not going to talk about this. This is a PV diagram, a pressure volume diagram. We're going to talk a lot more about that, hopefully in class when I see you. So don't worry about this cycle for now. We're going to talk about it later. But Carnot, if we had Carnot efficiency or maximum efficiency, our process would be completely reversible. That would mean that all of the heat flowing out of that hot reservoir is going into our engine. And of course we know that it can't be true because unless it's completely incredibly insulated, right, we're going to lose some of the heat to the surroundings. Also, there would be no friction between the piston and the walls as the piston moves up and down in this engine. Now, if it were completely reversible, we would have a different efficiency. The Carnot efficiency of an engine is E equal to 1 minus the cold temperature reservoir divided by the hot temperature reservoir. So notice these are not Q's. This is not the amount of heat that's flowing. It's actually a ratio of the temperatures. Now, if we go back to our regular efficiency, which is, and when we plugged in the value for work for QC minus QH, and we simplified, right, we had 1 minus TC over TH. So we can actually relate the Carnot efficiency equation to the regular efficiency equation. And so for a Carnot engine, the ratio of the heat that's being exhausted to the heat that's being input is equal to the ratio of the cold temperature reservoir to the hot temperature reservoir. So if the heat is all going into the flowing into the engine and coming out of the engine to the cold temperature reservoir, I will have maximum efficiency. Of course, by the second law of thermodynamics, that's not possible. So this is an ideal situation. Now, what this means, if we look at this efficiency then, is that the greater the difference between the temperature of the cold reservoir and the temperature of the hot reservoir are, the greater the efficiency of the engine is going to be, right? The more I separate these two numbers, the smaller and smaller this ratio gets, which means the more and more efficient my engine becomes. Now remember that, because I'm actually going to ask you a question about that in a sec. Well, let's look at a regular engine and what its real efficiency is, and then what its Carnot efficiency would be. So here is another engine. I have 890 joules of work going into this engine. I'm exhausting 690 joules of heat. Some work is being done. The temperature of the hot reservoir is 550 Kelvin, and the temperature of the cold reservoir is 290 Kelvin. So first question is, what is the work being done by the engine in each cycle? Well, again, remember, it's the difference between how much I put in and how much heat is flowing out. So 890 minus 690, of course, is 200 joules of of work that's being done. What is the efficiency of this engine? Well, the efficiency, not the maximum, but the actual efficiency of this engine, remember, is work, how much work is coming out, divided by how much energy we put in. So 200 divided by 890 joules gives me an efficiency in percentage, a percent efficiency of 22.5%. Not very efficient, right? I'm putting in a lot more energy than I'm getting work out. So if these are the temperatures of my reservoirs, then what is the Carnot efficiency of this engine? Well, the Carnot efficiency equation, 1 minus Tc over Th. So I'm going to take 1 and I'm going to subtract the ratio of the cold temperature reservoir from the hot temperature reservoir. So 1 minus 290 divided by 550, and I will get 47.3%. So even the Carnot efficiency of this engine is not that great, but better than the actual efficiency. If this engine undergoes 22 cycles per second, what is the power output? Well, first you got to remember, what is power? Remember that power is work. How much is the rate at which work gets done? Right? Power is work divided by time. Now, if we take the value of work and we multiply by the frequency of the cycle, then we could get that. Remember that frequency is the inverse of period, and cyclic, from a time standpoint, right, the time for one cycle would be like a period. So if I go through 22 cycles per second, right, that would be a frequency because it's the inverse of period, right? That would be seconds per cycle. So all I need to do here is take my 200 joules, right? That's the work being done, 200 joules per cycle, and I just multiply by the frequency, 22 cycles per second, and of course that's 4.4 kilowatts, or 4,400 watts, right? Unit of power is watts. All right, now my last question for you. If the theoretical efficiency of a Carnot engine is 100%, if that was even possible, then my heat sink, that cold temperature reservoir, what must its temperature be? Well, in order to get 100%, right, then Tc over Th has to equal 0, which means that the temperature of the cold temperature reservoir must be absolute 0. The reason why the answer to that is absolute 0, which is 0 Kelvin, and not 0 degrees Celsius, is something I failed to mention. When we do calculations with heat engine, or in gases in general, we will be working in Kelvin, not in degrees Celsius.